So we're going to continue on with this idea of Gaussian elimination and LU decomposition, and specifically start addressing some of the issues around stability of algorithms. So this is a really important thing, right? So a lot of us have learned how to do Gaussian elimination. And when we did Gaussian elimination sort of in sort of our class, the way we learned how to do Gaussian elimination, right, is you find the pivot, you go down, zero everything below it. And you already found in a theory point of view that you could get yourself in a spot that if you had a diagonal that was zero, you know you had to change it out. You had to change rows to make that thing work. And so we want to do something similar here in computation. Now, the problem with computation is even if you have a very small number that's close to zero, the computer will just do it for you because it's not technically a zero. And this can lead to numerical instabilities and an unstable algorithm. So I want to talk about stabilizing that LU decomposition, but basically doing pivoting. So this is a really important trick for us. And we already know it. We've already talked about it before. If you've had any kind of Gaussian elimination, you know that you had to pivot off a zero. And remember, with numerics and computation, it may not tell you there's a zero there because 10 to the minus 16 is not zero, is it? So you would divide by it. And that's where you get the source of some of the instability in the algorithm itself. So let me remind you what we did last time for LU. The entire goal of LU was to think about taking a matrix A and through Gaussian elimination, turning it into an upper triangular form, right? So we want to turn it into this through a set of operations. Let's call them L1, L2, all the way to L of m minus 1. So what we talked about in the last lecture is how to construct these matrices that when you hit it with A, they recursively zero out portions of columns in order to create this upper triangular matrix, right? So this is upper triangular. And this here is L minus 1. So we want to say this is the inverse so that if I can find, oops, just goes to there. So if I can find the inverse of that, then I'd have A is equal to multiply both sides on the left by L. I would get that. That's the factorization, right? So that's what I want to be able to do. Now, what does this L look like, or these L's that are part of this? Those L's, right, we constructed last time to look something like this. L of K was the identity minus L of K, and this is the unit vector in the kth direction, star. So this is an outer product. So this basically takes this vector, lays it on its side, takes an outer product with this L of K, which builds a matrix which you subtract from the diagonal. And what does this thing look like? Well, the L of K itself with zeros all the way up to the kth element, and then it's these L of K plus 1 K all the way to L of M K, where the L of K, L of JK, these coefficients here that you're going to be used inside of this matrix, these coefficients, the L of JK is equal to xjk over xkk. So these are the elements of the matrix itself, and xkk is the diagonal. Okay, so we were able to show how to construct this, and this is what we worked on last time, is to say there is a series of operations that zero out everything so that I can construct recursively. So the L1 makes all the zeros below the diagonal, all the elements below the diagonal zero in the first column. L2 makes all the elements below the diagonal 0 in the second column, and so forth. And this is the operation that, or the coefficient here. Now, the important thing here is on the bottom, you have an xkk. So if you have a 0 in the diagonal spot, this is going to be a divide by 0. And of course, we've known this forever. From when you took your first linear algebra course, if you did any kind of Gaussian elimination, you knew that you have to figure out how to pivot this thing, or else you divide by 0, which is not allowed. Okay? But in general, when you do computation, this isn't 0, but it could be something very small, like 10 to the minus 15. And in some sense, it's just very much like dividing by 0, because you can technically do it, but it creates a thing where this is now some very large coefficient because you divided by something exceptionally small. So this was the LU process. And what you would find for L, right, is L itself was when you inverse this matrix, you get L1 minus 1, L2 minus 1, all the way to Lm minus 1, inverse, product of these, where the L inverse of each k was equal to, we had this nice property, all you do is flip the sign of the L of k's here. So it's plus L of k E star k. So we worked all of this out last time. So this is how you do LU, or in some sense, how you've been doing Gaussian elimination this whole time, right? It's just but now it's in algorithmic form. It's more of a principled way. Before, when we did Gaussian elimination, you just thought about adding and subtracting rows until make things 0. But now this gives you a formulaic way to think about it as, oh, that's just a matrix multiplied. What matrices multiply this? This one. So this gets all the rows below it, sets all the zeros below the diagonal row directly, immediately to 0 by having this kind of formulaic structure. Okay, so that's very nice. So in other words, everything we did before can be put on a more firm foundation algorithmically. Okay, so of course the problem comes right here. So this generic application of the algorithm is unstable. It's unstable because you have this term here, which you're going to compute. And you ask the question, what if this is 0? Sorry. What if x of kk is equal to 0? The whole algorithm at least would break down in theory if it's 0, because you can't divide by 0. Okay? So that's what we're looking at, is that's the divide by 0 issue. But more than that, right, it's not just if it's 0. What if it's close to 0, right? So when we did Gaussian elimination by hand, we always said it has, if it's exactly 0, it's a problem. If it's non-zero, it's not a problem. And what we're saying now is, yes, but when we do computations, if things close to 0, it's still a problem. In other words, we can ask the following question. What if the size of that thing, the absolute value, take that there, is less than some epsilon, which is small? So it's much smaller than 1. So, you know, for instance, what if that thing is 10 to the minus 8, 10 to the minus 10? Okay. These are the kind of operations that lead to instability in the Gaussian elimination procedure. Because when you start doing this divide by a number close to 0, that error you introduce here now propagates throughout, cascades through all of these matrix operations. Okay, so that's what we're trying to figure out. Can we write the algorithm in such a way that we get around this issue? And of course, you already know the answer to that. The answer is yes. And you're going to do pivoting, because that's what you did in undergraduate linear algebra to get around this problem. When you have a diagonal element that's 0, you just switch some rows around and call it good. Okay, so that's what we're going to do here. All right, so let's go at it. Let's figure out how to get this thing done. So I want to draw some pictures first, and then we're going to modify these operations to account for this issue here. Okay, so let me draw some pictures here to hopefully illustrate it. So when I'm in my decomposing stage, matrix decomposing stage, not like me decomposing, but like I'm decomposing this matrix. Somewhere here, I'm at the kth diagonal. That's my pivot. And my goal is, right, at this stage here, when this is, I've got a bunch of elements below here, is what I'd really like to do is hit this now with L of k so that this thing here, right, at the x of kk, zeroes everything out. That's the whole goal, right? Take this, figure out this L of k, make all these zero. And the way we did that before is we had this factor here playing a role in zeroing all these out. But if this x of kk is zero itself, I can't actually construct an operator here because this thing becomes infinity because I'm dividing by zero. So the question is, what could I do? So what we really want to do is think about how would I modify this? And in fact, you could imagine instead of making, picking this, making everything zero, you could actually pick any component of this vector here from the diagonal downwards. In fact, let's go down here and say I pick the ij one below here. And I could say, let's actually pivot on there. Let's actually make everybody else zero. So one imagines that you could just say, let's redo this, but at the xkk position, I'm just going to actually go ahead in that column. I'm going to say xij is the one I want to keep, and I make everybody else zero. So I'm really morally doing the same thing I did here. Okay, it's just that here it is. I just made this everybody else zero except for the diagonal, some x of ij. The problem with this is, yes, you could randomly do this, but what we want really is some principled way to do something like this so that we can still end up back here with our LU decomposition in an algorithmic way that we just run a code. It actually does all of this for us directly. Okay, so that's going to be the goal in stabilizing Gaussian elimination and LU decomposition. Okay? All right, so what we learned in Gaussian elimination, by the way, is that when we did the Gaussian elimination, we put the matrix in augmented form, we learned that you could actually switch any rows without any problem. It's not a big deal, right? So every single row of the matrix corresponds to a set of equations, and presumably they were put there in some order, but any other order, it's still the same governing equations. And so switching rows is trivial to do, right? And how do you know you put the rows in the right way, right? Because what happens if you get to a divide by zero? You could say, well, is that anything to do with the problem, really? No, it's just the way you actually inserted maybe those rows. You ended up with a divide by zero or divide by some very small number, and it's completely artificial. It has nothing to do really with the solution. It's just that you arranged perhaps potentially these rows in a bad way. So here's what I want to do. How do we come back to this then and start algorithmically to construct a more stable way to do this reduction? Okay. So let's go back. I'm going to draw this matrix again, a little bit bigger this time. And I'm somewhere here in the xkk. So this is essentially my pivot, and I have a bunch of numbers below it. And in fact, one question I could ask with all these numbers below it, what I'd really like to do is I would like to avoid dividing by 0. So in other words, when I take this thing, what I'd really like to do is figure out, well, how would I switch rows to avoid this issue right there? How do you do the selection? So one thing that's problematic is if you divide by very small numbers, that's problematic. But if you multiply by very small numbers, doesn't matter. Or in other words, divide by a big number. And in fact, what we could do to do a selection here is just go find out of all these elements, which one's the biggest. And I will use that as the pivot. Okay, so in other words, let's say somewhere in here, there's an xij, and this is the largest of all these components here. Okay, so that's the largest value of these components. Okay, so let's call this vector here c, and then so xij is the max of the vector c. Okay, so I'm going to go pick this, and what I'd really like to do then, first thing is to take what I have here, and I want to switch this row with this row. So I'm going to do a permutation operation at this point. So what I needed now is a matrix that does permutations that will switch rows for me. So I want to hit this with a permutation matrix. It's called P of K. That what it will do is we'll take this and now switch these two. So right here, I have x of ij, and I get the x of kk here with all the other values. So all I've done is I've switched these two. So that went here, that went there. And you ask the question, what is the matrix P that does this? We'll address that in a minute. But once we have this, then I want to hit this now with L. Now that this is the biggest term here, what I'll do now is I will zero everything out below it. So now I hit this with L of K. And now what you have is xij zeros below it. That's what you get. So notice now, instead of what we did previously when we did Gaussian elimination, right? We just simply went down this process, find out each L of K that zeroed everything out. What we're actually doing at each step is we're looking at all the terms below, at the diagonal, everything below, find the maximum, switch rows, now hit it with L of K. Okay, so the operation is two steps. Hit it with P of K, L of K, at each single step in this decomposition. So this is what I want, P of K, L of K. That's the step. Permute it, permute it, then multiply by L of K. That's what we want to do. So this is what replaces what I was doing before, which is I just did L of K, and now this should go to this, which is permute it first, then hit it with L of K. So that's going to be the process that's aiming towards stabilization, making this Gaussian elimination, this LU procedure, as stable as possible. What you're doing here is walking yourself away from any terms that might be small here so that you don't get into a divide by a small number issue, which is what's ultimately can lead to a cascade of propagating errors in the system and in ill-conditioned algorithm. Okay, so of course the numbers have to be very small, right? This is the problem. But if you generically don't look at your matrix, even a number like 10 minus 10, clearly not 0, this will just work, but it's going to give you sort of instability in computing these numbers here, okay? All right, so how do I determine the P of K? what is that permutation matrix? How do we construct a permutation matrix? And this is actually very easy to do. So I'm going to erase this. So hopefully now you see what I've done is just replaced this one step with now two steps. At each step, I'm going to go look at the, instead of just taking that as the diagonal, I'm going to go look who's the biggest, move, switch the rows, now do that step of making everything zero below. And so now we're just pivoting everything, not just things that are zero, but anything. We're doing a pivot at every step. Even if this is like 1, if that's 100, move that up. Okay? So that's what we're going to do. And the question is, how do I construct the permutation matrix? And they're pretty easy to construct. What is P of K? All P of K is you take the identity matrix, which is ones on the diagonal, and if I want to switch the jth row with the kth row, all I do in this identity matrix is switch those rows. So normally there'd be a 1 here. This row moves up to here, and the one that's here moves down to there. So this here, right, is the jth row. This here is the kth row. And this kth row now is in the jth row. And this jth row now is in the kth row. So you just switch these two rows. That's it. So you go through, you do your search, you find where the maximum is. You say, oh, this is in row K. And you say, all right, if that's in row K, I want it now to be on the diagonal. So then I just move it up to the diagonal. I just take that identity matrix, switch the 2 appropriate columns. You're done. That is the permutation matrix. Okay, so how does it work in practice? Well, if you remember, when I'm doing this decomposition, and I'm here at x of kk, and there's some x of ij here, and this is where I want to be operating. What I really want to do is say, okay, if this is where the maximum is here, this xij, this is in the ith row, and I want to switch it with the kth row, then what I would do to construct this P of K, then I would just basically say, okay, go to from the kth row, put this kth row in the ith row, and the ith row in the kth row, which just you would do exactly something like this. So you just go and pull them out. And in MATLAB, this is pretty easy to do, or Python, right? You just build an identity, and you just go grab the jth, overwrite it into the kth row, and kth row into the ith row. That's it. That's as simple as you need. And what it does for you, once you've done that, right, it's going to take that matrix, and it's going to take this x of ij and put it in that slot, and the x of kk will be down here with all the numbers. And now you're ready to hit it with your L of k that we built in class last time. And what's nice is this is the biggest diagonal value available to you. And so in some sense, it's the most stable way to construct the LU decomposition. Okay. All right. So that's kind of the generic structure of thinking about pivoting. And now instead of just pivoting once in a while, like whenever we had to divide by 0, like we did in undergraduate linear algebra, what we're doing now is constructing an algorithmic framework for automating this process. Not just automating it, but doing it at every single step, right? Why would you just do it when you have a divide by 0? Because again, when you're dealing with real data, you're never going to really have 0 in there. You're going to have maybe some really small numbers. And so when you do this operation with the LU, it may not complain. Even if there's a small number like 10 minus 10, that's not divide by 0, that's divide by 10 minus 10. And so what this allows you to do is say, I'm going to get around any kind of issues like that, stabilize LU by just simply going for each row, for each different pivot, trade it out to the largest value, do the L of K, trade it out for the largest value, do the L of K, and recursively do this to generate your most stable algorithm for building an LU. Okay? All right, so let me write down our modified algorithm then. And the nice thing again is these P of Ks are really easy to build. I mean, they're just permutations of identity. And if you can convince yourself, you multiply that by any vector and it'll just switch the two components that you've switched here, will switch those two components in the vector, which is exactly what we want. Okay, so what does this mean in practice for us? If you remember what we had before for the LU is we had a sequence of matrix multiplies acting on A to get us into this upper triangular form. But now what we want to do is, before I hit any of these L1s, L2, all the way to L of n minus 1, I want to do a permutation. I want to move out of all the possible, all the things I'm trying to zero out, that whole vector, I want to go ahead and look at it and say, which one is the largest, move it into the pivot spot, and then zero things out. So this is going to be modified for stability's sake to the following. Now, instead of L1, you first permute, then you hit it with L1. Then you permute, hit it with L2, all the way Ln minus 1, P n minus 1. So you see now, what I've done is I've added all these matrices in here, which are permutation matrices, acting on A to get to U. So pivot first, then zero, right? So that's the idea. Pivot, and then you zero out. Pivot, zero out. Pivot, zero out. That's the more robust, structured way to do it. Of course, this will cost you a little bit of extra time, right? Because now you're going to have to go look who's the maximum value, switch rows, one extra operation in there, matrix multiply. But what it buys you is a lot of stability properties, and you don't have to worry about, like, am I in a situation where I'm propagating some number where I divided near zero. Okay, I want to show you a couple. I'm not going to work out the linear algebra here, but it's not that hard to show for yourself, and so we'll just go ahead and show you some of this, and then we'll go from here. So now I have this as my operation, and if you remember, this here is like my L minus 1. And so I still have to invert now this whole thing. Now before, it was very easy to invert this because when you inverted it, you had L1 inverse, L2 inverse, which all you had to do is for that LK is flip the sign of the L of K. That's it. Super easy inverse. But now we have to rearrange this, and you're going to see it's a little harder, but still not so bad to do. In fact, you can rewrite this, and like I said, I won't work out the algebra for it, but this is going to be rewritten as a product of the following form: L minus 1 prime, L minus 2 prime, all the way to L2 prime, L1 prime, times Pm minus 1, Pm minus 2, P2, P1. So this L minus 1 can be written as this product here. Now notice what I've done with this. I've moved all the P's to the right. So in other words, I took up all these permutations here on the right. I multiplied them all out. And on the left, I now have versions of L1 and L2. In fact, let me write down what these L's are. So L1 prime, L minus 1 prime is just equal to L minus 1. So that's the same. the L2, L minus 2 prime is equal to permutation M1, LM minus 2, permutation M1, negative 1, and so forth. So there's an explicit formula that allows you to have these nice structure here, which allows you to do this inversion in a very nice way. Okay. All right. So this is nice because then what you have is this set of L's, this set of permutation matrices all together. All right. All right, so that's, oops, I dropped that. So this is some linear algebra tricks to compute all this. But you can see it's familiar. It's very similar to what we've done, but we've made some modifications to all of this in order to make it work here for the LU. And you can find that it's actually not that hard to compute the inverse of this or the inverse of this, because this is what we want is L itself. Okay, let's finish this off here and talk about where we're going to go with this. So I have this decomposition. I've now explicitly computed a pivot at each single step by just looking at who's the maximum along that vector I'm trying to do elimination on, move the maximum up into the pivot position, redo the computation. And this is the algorithm for doing it. I want to now come back to AX equal to B, because that's actually what we were trying to solve, right? So there's an LU decomposition of a matrix, but really we were doing that LU with the goal of solving AX equal to B. So let's talk about how this is going to come to play in solving AX equal to B. And in particular, what we're really saying is that, notice that we're not doing an LU decomposition anymore. What we're really doing is this permutations on A gives me some LU. That's what we're really done here. I've got a set of permutations acting on A, which are given by here. And then I'm going to invert this to take to the other side to be the L. Okay, so I actually want to invert this piece here. So I'm gonna take that out, because actually I don't want to inverse this. I just want to invert this guy to the other side. I'll leave the P right here. So take P, hit A with it. What does P do on A? It shuffles the rows. And it shuffles them in such a way so that when you do the Gaussian elimination, you walk down that diagonal, you're always getting the largest possible diagonal value. Okay, that's it. That's what the P does. And then you do the LU. So how does this play out for us? And P, by the way, is the product of all these guys together. All the P of J's. That's what this is. So P handles every single shuffle you did. Every single time you shuffle the rows, columns, this is keeping track of all of it. And so it basically is the grandmaster of shuffles. Keeps track of all of them, and you have it. So now let's talk about AX equal to B. Notice here, when I go to try to solve AX equal to B, I don't have A anymore. I have P of A equals LU. So really, I want to multiply both sides of this by P. So I get P of A x is equal to P of B. And then you do an LU here. LU x is equal to PB. Let's call this our B hat. So notice what I've done here. My right-hand side, B. So when I go solve AX equal to B, and I'm doing this by LU decomposition, if I have the LU of this, we did an upper and lower triangular solves. In other words, forward and backward substitution, get our solution for X. But if I've shuffled all these rows, B better also shuffle the same rows. So that's what this does here. I have to multiply P on both sides. P on this side, P on this side. So this is a new vector. It's taking the vector B, shuffling it the way I shuffled A to get the LU. And then I solve this. So that's the idea of how you would do this LU factorization to stabilize this algorithm in practice, right? You just want to say, I'm going to go through, and if I want to stabilize this, I should pivot everywhere I can to make this thing more stable. And this is one way to do it. One way to do it is to say, go find the largest possible value to sit inside of that diagonal. By the way, if you don't do that, you could imagine, like I could just instead come up with a different rule. You know, as long as the pivot is bigger than 0.1, fine. If it's less than 0.1, shuffle it. Go find the largest, then shuffle it. Then occasionally you'd have a P, but you'd still have to keep track of it here. You'd have to keep track of a P so that you multiply the right-hand side by it, and you get this. And so all I'm showing you is ultimately exactly what you did in linear algebra for solving Gaussian elimination, which is every time you hit a 0, you shuffled rows. And this is an algorithmic way to do it, but it's even better because it also handles anything close to 0, anything small. It's giving you the most stable version in some sense of LU because you're always putting the biggest value sitting right there on the diagonal. So you avoid any kind of problems with dividing by small numbers. And that is your stabilized version of Gaussian elimination and LU. And like I said, this week we are talking about solving X equal to B. And so we're hitting these things, which are things that you did actually in linear algebra. And now here's sort of your algorithmic way to think about that stabilized version of Gaussian elimination.